Okay, so this is where we left off. We've got this right here, which remember was representing the Laplace transform of f times the Laplace transform of g. Okay, so it was a product of two Laplace transforms. We've determined that it's going to be this lovely double integral. And it's set up so that we're integrating first with respect to t while we hold u constant. So I was illustrating earlier, if u is constant, we'd be at some fixed horizontal line, because we're at some fixed height, okay? And then for that constant, our limits of integration where t is going from u to infinity. So this was the line t equals u. We would start on that line and then keep going and let t go off to infinity. So the starting value for t is going to be different depending on what the value of u is. Now what we're hoping to do is to keep the integrand the same, f of t minus u, g of u, e to the negative st, but switch the order in which we're integrating so that we can do a du first and then a dt. Now, if we do that, we're going to have to figure out what are the limits of integration that still describe this same region. The idea is now, instead of for each fixed value of u, we have to figure out what t varies from and to. For each fixed value of t, we have to figure out what u varies from and to. So if t is fixed, I'm talking about basically a vertical line here, okay? And I can see that for this value of t, my u values are varying from 0 to the u value on this line. But this line was the line u equals t. So it looks like u is going to go from 0 to t. Let's just make sure that works at other places. If I have a different t value, I'm in this region between here and here. This is a u value of 0. The u value on this line is t. So for each value of t that I have, u is varying from 0 to the u value on this line, which is t. So u is just going to go from 0 to t. And then what t values do I have to do that for? Well, it looks like we start at 0, where here I've got a very small window of u values to worry about because we're going basically from 0 to 0. And then as I move to the right, the interval of u values that I have to take into account gets taller and taller and taller. Looks like t is going from 0 to infinity. So there we have successfully switched the order of the integration. Again, something that I think even if you haven't had 3C, you can sort of see what we were doing and follow the explanation, but I wouldn't expect you to reproduce it without taking a full class in how to do this stuff. Okay. All right. So now, one more time, I'm going to factor out a constant. This has no u's in it. So this is constant with respect to u. So I can pull it outside of that inner integral. So I can say this is the integral from 0 to infinity of the integral from 0 to t of f of t minus u times g of u du, and then I've pulled out that e to the negative st dt. Okay, so this is now an improper integral from 0 to infinity of this thing, which is a function of t. The upper limit of integration is going to be the variable for this thing. U is just a dummy variable. This function of t multiplied by e to the negative st dt. Well, that exactly matches the formula for the Laplace transform of this thing, this function right here. So that function has a name. We call it f star g, and it's the convolution of f and g. And so we are able to say now that this product of these two Laplace transforms, which is what we started with, which gave us this crazy double integral, I can now view this as just the Laplace transform of the convolution f star g. Which means if I then take the inverse Laplace transform, I'm going to get that convolution. Okay. So I can basically say the inverse Laplace transform of the Laplace transform of f times the Laplace transform of g, this product of things, is just going to be the convolution f star g. Now, I think it's well named. It's kind of convoluted, okay? But it does give us a nice pattern. It might be a kind of complicated pattern, but it does give us a consistent pattern for what we're going to get if we try to take the inverse Laplace transform of a product of two Laplace transforms. Again, why we might want to do this is not yet clear. I think what we're going to do in the next video is just practice actually calculating a convolution, because it is a little bit of a convoluted argument. So we'll practice calculating that to see that u really is a dummy variable and this does just become a function of t. And then we'll take a look at some differential equations that we can solve by using convolutions. Basically, it's going to be useful when we have a family of differential equations and we want to try to look for a pattern or some relationship between those family members so that we don't have to go through the same steps again and again and again to solve each differential equation from each member of that family. All right, so that's where we're going.